Hi everyone, Mr. Rolf here, and today we're going to talk a little bit about polarity. And in order to understand polarity, what we really need to understand is that polarity only occurs in covalent bonds, all right? So in the last unit, we kind of talked a little bit about how these atoms will either maybe give and take in the case of ionic bonds, or in the case of covalence, they're sharing, right? So in order to talk more about this idea of polarity, we need to understand electronegativity. So electronegativity is really a measure of how much pull an atom has on the shared electron. So what we end up finding is that these atoms don't share equally. So, obviously there's like a, if you share your toys, maybe, you could play with it 50% of the time. I could play with it 50% of the time. Well, with polarity and with covalent bonds, that's not the case. Sometimes there can be a little bit of a bully, and you notice down here, you seniors, seniors are usually the big bullies, and I'm referencing here the tug of war that typically occurs, say for homecoming assembly. Those seniors are usually just really pulling on those, in this case, electrons in the tug of war, and our poor teachers, our little hydrogen here, just can't keep up. So when you look at this reference sheet, you'll notice we're going to talk about this part a little bit later on, not today. We want to focus really on this right here. So this is really a list of how electronegative these elements are. So what you'll notice is that our most electronegative element, there's our big bully, fluorine. Okay, so fluorine really, really wants electrons. You might remember that from earlier. And then something like cesium doesn't want electrons. It really wants to get rid of an electron. So it's kind of wimpy. It says, here, take this electron. I don't even care, leave me alone. So fluorine, on the other hand, is our big bully. So anything closer to fluorine is going to really start to rip electrons away. It might share, but it's not going to be equal. So, and then we'll also be using this table down here. So when we look at two atoms together, for example, fluorine and cesium, if I were to try to put those together in a bond, which we would see is that we're going to take the difference, all right? So we take the difference, and in this case, 4.0 minus 0.7 gives us a difference of 3.7. Oh, man, that's off the map. These two rarely come together. So this would be a super ionic bond, if you would. Obviously, this list is not all-inclusive. So let's look at the different types of bonds. We just kind of looked at one. It was ionic, but let's look super ionic, in fact. Let's look at this. So the first one we're going to look at is a nonpolar covalent bond. So if it's nonpolar, that means that the pull on those electrons, when they share, so for example, let's just look at this example right here. If I look at this individual bond between carbon and hydrogen, that is a nonpolar bond. It means that the electrons that are being shared between the carbon and the hydrogen are being shared equally. You can almost envision those electrons in the tug of war. Those electrons are right smack in the middle. It's, nice sharing, if you will. So let's just look at those two elements on our table here. So I had hydrogen, and then I also had carbon. So when I subtract those two, 2.5 minus 2.1, or if you do the other way around, we'll take the absolute value. When I look at that on the table, a difference of 0.4 tells me that it is a nonpolar bond. And if I take and look at the other bond in that, the only other bond that could be there, right, we said between carbon and hydrogen, there's carbon and hydrogens all over, but look, we also have carbon and carbon. However, if it's the same element, right, a carbon minus a carbon, well, that difference is going to be 0, right? So that still is a nonpolar bond. So all of the bonds in that molecule are nonpolar, so that overall, that's going to make a nonpolar molecule. So let's look at something that is polar. And another word that I want you to keep in mind when we say polar is I also want you to think about this word right here, charge, all right? So when we say polar, that means that it's charged. There's a positive end and there's a negative end. This happens when these when these electrons that are shared, but they're not shared equal. So there's a bully, there's some atom that's holding those electrons a little bit closer. It's kind of like, here, you could borrow this, you could play with this toy, but only for a second, and then I'm going to take it back. So when we look at this, at these two atoms, in this case, I have hydrogen and I have oxygen. So let's just look at this bond right here, because obviously it's the same for both. So when we look at the next, back to our chart, when we come back to our chart here, we see hydrogen is still at 2.1, and then oxygen is at 3.5. So when I subtract those, 3.5 minus 2.1 gives us 1.4, and that tells us that it is a polar bond. All right, so polar means that it's charged. So what we can do to signify that it's polar is we can say that the electrons are going to be hanging around that oxygen, all right, because oxygen is the more electronegative atom. This oxygen, we said, has an electronegativity of 3.5, and then our poor oxygen over here was only 2.1. So what we can do is we can use these symbols. This is a Greek symbol, I believe it's sigma, that tells us where the negative, where the electrons like to hang out. So in this case, since 3.5 is more electronegative than the 2.1 on hydrogen, that means the electrons are going to hang out around this oxygen. So what we do is we signify that with this symbol, this sigma with a negative. So that means partially negative. So when we look at this atom, the oxygen side of the atom, because all the electrons are over there, you can almost imagine these negative electrons, that side of the atom is going to be a negative side. And then the hydrogen side is going to be partially, we say partial, partially positive. Okay, so you can almost picture overall, we have a positive side, and then we have a negative side. So it almost acts like a magnet. So we started off with an ionic bond in that first example with cesium and fluorine. And really what an ionic bond is really just a superpolar bond. So it means that the bully is just stealing at this point, right? So in this case, here's our poster child again. Sodium is giving up that electron because chlorine is just ripping it away. So if we relate that back to our table, what you'll see is we had Na, here's Na at 0.9, and here's chlorine at 3.0, chlorine being the big bully that it is. And the difference between those is going to be 2.1. 2.1's not on my sheet, but you'll see that really this is just kind of like a scale. There's obviously shades of gray as far as how polar something can be. Something could be superpolar, and that would be ionic like we're talking about. Or it could, on the flip side, it might just be a little polar if it were to maybe have a difference of 0.04 or 0.5 or 0.4. So just keep that in mind, that these aren't just like boom, all of a sudden it's superpolar, or boom, all of a sudden it's nonpolar, it's not charged. There's definitely varying levels of polarity. So hopefully you learned a little bit about polarity. If you have any questions, please obviously talk to your instructor. Thanks.